All right, let's talk about something incredible. We're going to dive into the electric language of your nerves, how your body sends these lightning-fast messages using a crazy cool mix of electricity and chemistry.
I mean, have you ever really stopped to think about it? You decide to wiggle your toe, and bam, it happens. That signal travels from your brain down your body in an instant. It's an absolutely mind-bogglingly fast network. So, how on earth does it actually work?
Well, to get to the bottom of this, we need to meet the hero of our story, the neuron. And the first thing you need to know is that even when it's not resting at all. It's charged up, like a coiled spring, just waiting to be released.
Okay, so this is our guy, the neuron. Think of the dendrites as its ears, always listening for incoming signals. The cell body is the brain of the operation, deciding if the signal is important enough. If it gets the green light, the message is blasted down this long cable, the axon, all the way to the axon terminals. And from there, the message gets passed to the next cell in line. It's a super elegant and efficient setup.
Now, this is where it gets really cool. We call this the resting potential, but honestly, that's kind of misleading. Because this neuron is not resting. It's burning energy to create an electrical imbalance, essentially turning itself into a tiny, fully charged biological battery.
So, how does it build up this charge? Well, it's all about a little game of tug-of-war with charged particles called ions. Let's just imagine for a second that only potassium ions, K+, could move. There's a ton of potassium inside the cell, so it would naturally leak out, leaving the inside with a really negative charge, specifically negative 94 millivolts.
Okay, now what about the other team? Team sodium, or Na+. There's way more sodium outside the cell, so if only sodium could move, it would rush in, flooding the cell with positivity and jacking the charge all the way up to a positive 61 millivolts.
So you've got this massive tug-of-war, right? Potassium's trying to drag the charge way down to negative 94, and sodium's trying to pull it way up to plus 61. So who wins? Well, the referee here is the cell membrane itself, and it's kind of biased. It's about 100 times easier for potassium to leak through than it is for sodium. That gives Team Potassium a huge advantage. So, when the dust settles, what do we get? You factor in that massive influence from potassium, plus the tiny bit of sodium that manages to sneak in, and the neuron finds its balance at about negative 90 millivolts. And that, right there, is its stable, ready state. It's primed, it's charged, it's basically sitting on a powder keg, waiting for a spark. Okay, so we've got our charged up neuron just sitting there at minus 90 millivolts, ready to go. Now, let's talk about the spark that lights the fuse, the moment that neuron decides it's time to fire.
This is really the big question, isn't it? What's the trigger that takes it from ready to go? You have to understand it's not a slow burn. It's an absolute explosion, a lightning-fast event.
The magic word here is threshold. The best way to think about it is like the trigger on a spray bottle. You can press it a little more, nothing happens. But the second you press past a certain point, whoosh, it fires completely. For our neuron, that point of no return is about negative 65 millivolts. If signals push its charge up from negative 90 to negative 65, it's game over. An unstoppable chain reaction is about to begin.
And man, what a chain reaction it is. That little nudge up to negative 65 millivolts is like tripping the first domino. It springs open these special doors or channels just for sodium. Sodium ions pour into the cell, making it more positive. And what does that positivity do? It opens even more sodium channels. It's this incredible, explosive cascade of positive charge flooding into the neuron. And this whole explosive event is governed by one simple, really important rule, the all-or-nothing principle. Basically, a neuron doesn't have a volume knob. It can't half-fire or whisper a signal. It either fires with 100% of its power, sending that signal screaming down the line, or it doesn't fire at all. It's on or off, a 1 or a 0.
All right, the fuse is lit, the rocket is launched. So now let's actually ride that electric wave, what we call the action potential, as it zips down the length of the nerve.
This whole journey happens in like 3 quick acts. First, depolarization. That's the big explosion, right? The sodium rushes in and the charge flips from negative to positive. Then comes repolarization. The party's over, the sodium channels slam shut, and now potassium channels open up so positive charge can rush out, bringing the voltage back down. And finally, you hit the reset button, where a special pump cleans everything up to get ready for the next signal.
And I cannot stress this enough. The speed here is just mind-boggling.
We are talking about a process that happens in a few 10,000ths of a second. It is unbelievably fast. The sodium gates fly open and then start to slam shut in a fraction of a millisecond. Right as that's happening, the potassium gates are opening wide to reset the whole system. It's a perfectly timed microscopic dance.
So you think that's fast? Nature figured out a way to make it even faster. And the answer is insulation. It's a fatty stuff called myelin. Think of it like the plastic coating on an electrical wire. It wraps around the axon, and instead of the signal flowing smoothly, it forces the signal to jump from one little gap in the insulation to the next.
And the difference this makes, it's not small. It's absolutely insane. An uninsulated nerve fiber might send a signal at about half a meter per second. A slow walking pace. But a properly insulated, myelinated fiber can shoot that same signal at 100 meters per second. We're talking about going from a slow jog to the speed of a Formula One race car. It's an incredible biological upgrade.
Okay, so our super fast electrical signal has screamed down the axon, but now it hits a roadblock. There's a tiny little physical gap between it and the next neuron, called a synapse. The electrical signal can't just jump across, so what does it do? It pulls off a really clever trick. It changes the message from electrical to chemical. Here's the handoff. The electrical pulse gets to the very end of the line, and that rings a doorbell for another ion, calcium. Calcium floods in, and that acts as the trigger. It tells these tiny bubbles that are filled with chemicals, neurotransmitters, to go to the edge and release their cargo into the gap. Those chemicals then just float across and fit like keys into locks on the next neuron. And those little chemical messengers can carry one of two basic instructions: go or stop. An excitatory one is like a green light. It opens channels that make the next neuron more positive and push it closer to firing. An inhibitory one is a red light. It makes the neuron more negative, pushing it further away from its firing threshold. It's this beautiful balance of green lights and red lights that allows for all the complex processing in your brain. So the message is sent, job done, right? Not quite. After the party, you got to clean up the mess. The neuron just went through this massive ionic upheaval, and now it has to reset everything so it can get ready to fire all over again. It needs to recharge. And the unsung hero of this whole operation, the cleanup crew, is this amazing little molecular machine called the sodium-potassium pump. It's this tireless worker that after every single signal fires, it immediately gets to work, actively pushing sodium back out and pulling potassium back in. It's what reestablishes that perfect negative 90 millivolt resting state. And this is why just thinking burns calories. That little pump doesn't work for free. It needs energy in the form of ATP to do its job. It's constantly working. In fact, even though a neuron can fire an insane number of times, like 50 million times before it's totally depleted, this constant recharging process is one of the biggest energy drains in your entire body. Your brain is a power-hungry organ, and this little pump is a huge reason why. So think about that. We've just walked through the life of one single nerve impulse, one tiny electrical note in a massive orchestra. But right now, as you're listening to me and processing all of this, there are literally billions of these signals firing off in your brain, creating this unbelievable, perfectly coordinated symphony that is your thoughts, your feelings, your consciousness. It's just wild to think about, isn't it? What does that incredible electrical music inside your head sound like at this very moment?